Alright friends, welcome back. In this video we're going to go ahead and cover the next section of your prerequisites chapter, which is P.4. We're going to take a first day for this and talk about a couple of different things as far as factoring polynomials is concerned, and then in the next video, day 2, we'll go ahead and finish up factoring, get some practice in, and yeah, after that we'll move on to the next section like always. So in this video specifically, we are going to start to kind of reintroduce you to this idea of factoring a polynomial, okay? But I only want to take a look at a couple of different things that show up in this little checklist that I've left here in your notes, right? So today specifically, we're going to go ahead and take a look at doing the first step of factoring, which is to always look for a GCF. And then the second step of factoring is to count the number of terms, and keep in mind those are separated by plus or minus signs. And then depending on the number of terms, you proceed in a certain way. And so what I want to do is just specifically this second one where we have two terms that are polynomial. So we're going to talk about how to look for these different forms, a difference of squares, a sum of cubes, or a difference of cubes, okay? We're going to save the 3 terms and the 4 terms for the video after this one, so stay tuned for that, okay? So what I want to do is first go ahead and take a look at factoring out a GCF, and then we'll talk about some of the things that you need to keep in mind for that, and then after that we'll move on to some problems where they have 2 terms and we'll factor them using one of the forms, okay? So let's go ahead and hone in on this first example here. It says factor the given polynomial completely, okay? So number 1, it says 6x cubed minus 4x, and here's the way that I think about factoring, right? When this was first introduced to you, your math teacher may have introduced this in a certain way, but here's how I always do it, right? First of all, I'm going to identify how many terms I've got, right? And they're always separated by plus or minus signs. So I'm seeing this big minus sign in the middle, so that tells me that I've got 2 terms in this example, okay? So let me go ahead and set some of my things up here. So I've got a big minus sign, and then I've got 1 term minus another term, okay? What I typically like to do is I like to write the GCF that we're going to factor out, the greatest common factor. I like to write it under both of my terms because then it's just kind of set up and ready to go for me in terms of thinking about what I'm going to have left over after I factor that out, okay? And so we are going to go ahead and write this on the other side of an equal sign, but take a look at our 2 terms here. We've got coefficients of 6 and 4. So when you factor out a GCF, remember that's called a greatest common factor. You're looking for a common factor of 6 and 4, but you're also looking for the greatest one. So the biggest common factor that you can factor out of a 6 and a 4, I believe, is going to be a 2. Okay, 6 and 4 are both even numbers, and so as far as common factors that they're going to have, looking for the greatest one, I believe that's going to be 2. And then I'm moving on to the variable terms. Okay, so in the first term I've got an x to the third, in the second term I've got just a single copy of x. We're looking for the greatest number of copies of x that both of these terms can have factored out. And so because that second term can only factor out a single x, that is what I'm going to factor out of the first term as well. Again, common factor, okay? And so it looks like here the monomial 2x is going to represent the GCF in this problem. And so what I want you to do is I want you to write it as the GCF times what I'm going to oftentimes refer to as the leftovers, okay? So that's not very professional mathematics language here, but the idea is going to get across, right? When we factor out the GCF, we're going to be left with this expression that we have left over, and I typically am in the habit of just simply calling those the leftovers, okay? And so what is leftover? Well, this is exactly why I like to write this as a division problem with my GCF, is because now it's super easy to go through and first of all just take care of these coefficients. So I've got something like a 6 divided by 2, that's going to leave me with a 3, and then move on to your variable terms here. I've got x to the third divided by x. And so remember, when we divide like bases, we subtract the exponents. And so that would be 3 minus 1, or in other words, x to the second power, okay? And then there goes my big minus, and then we're going to move on to the other one, okay? Do the exact same thing, and I won't be as colorful or as meticulous about this in future examples, but I just want to get the point across. So 4 divided by 2 is, of course, going to be 2, and then if you look at those variable terms, those are actually just going to cancel out for us, right? We have an x on the top, we have an x on the bottom, and so those are going to cancel for us straight away. And so we're just going to be left here with that leftover expression, that 3x squared minus 2, okay? It would be at this point in future examples where we would want to look at our leftovers and determine if they can continue to be factored, okay? But here I don't believe that that's going to be the case, so I'm just going to go ahead and box what I've got here as my final result. And so, again, you always want to write it as the GCF times the leftovers in parentheses. And then we'll just take a look at a couple more examples here, right? So in this next example, number 2, I've got 3 terms. I've got a big minus, I've got a big plus, and then I've got 1, 2, 3 terms here, okay? And again, we're going to play the same game. We're going to look at all the coefficients first. We're going to determine if they have any common factors and then take out the greatest one, and then we're going to move on to the variable terms. So if you look at the coefficients here, I've got numbers like 4 and 12 and 16. These are all numbers that have a common factor of 4 in common, and because we have a single term that is 4, I believe that's going to be the greatest one that we're going to be able to pull out. And then we'll move on to our variables. We'll notice here that the second term has an x in it, the third term has an x squared in it, but the first term doesn't have any x's. And so because we're trying to factor out something that all 3 of these terms have in common, well, all 3 of them together don't have an x in common, and so that means that the x will not be part of my GCF. So the GCF here is just simply going to be 4. And then I'm going to go ahead and write that times my leftovers like always. So again, we set this up as a division problem. 4 divided by 4 is 1. 12x divided by 4 is 3x, so I'll say minus 3x. And then there goes my big plus. If I have 16x squared divided by 4, that's just going to leave me with 4x squared. Okay? And then there would be the simple matter of rewriting this in standard form, which we could totally do. This would be 4 times 4x squared minus 3x plus 1. Remember, we talked about standard form in the last video is when your polynomial is written with decreasing powers of x. Okay, so we start off with our x squared term, followed by our x term, followed by our constant. In this third example here, we have more variables, but nothing changes. We still identify here that we have 2 different terms, and we still want to look at what they have in common. Well, I have numbers like 2 and 4. I could pull a 2 out of both of those. Moving on to my x's, the first term has a single copy of x. The second term has 2 copies of x. The most copies that I can factor out that they have in common is just a single copy. And then it's the same thing with those y's. The first term has 2 copies of y, but the second term only has 1 copy. So I'm going to factor out only a single copy of that y. So my greatest common factor here is the monomial 2xy, and we'll write that as times the leftovers here. Okay, well, if you do the divisions on this, this is going to be 2y, because if you look closely, the x's are going to cancel out there in the first group. Okay, and then there goes my big plus, and then 2 over 2 cancels, y over y cancels in that second term, but I have an x squared over x, and so that's going to be just a single copy of x, and that's going to represent my factorization. Okay, so once you factor out the GCF and write the leftovers, take a look and see if your leftovers can continue to be factored, but that was an example where they didn't, of course. And then here we've got 3 terms here. We've got a big minus, got a big plus. We got 1, 2, 3 terms. And in terms of what they all have in common, at least as far as the coefficients are concerned, we've got numbers like 3, 5, and 4. These are ones that don't have any common factors. So we're going to move on to our x's. And it looks like the largest numbers of x's that all 3 of these guys can give up at the same time would be just 2 of them. So I'll say x squared is something that all 3 of these can get factored out, and then we'll move on to the y's. You'll notice that that very last term doesn't have any y's in it, so we're not going to be able to factor out any y's here. So our GCF is just simply going to be x squared. And then we'll go ahead and write that as times our leftovers here. So again, just doing this quick divisions here, you're going to have 5y minus 3xy cubed plus 4x squared. I'm just going through, I'm doing those divisions, and then writing what I would get left over there. So there is our result for that one. Okay. Number 5 is a little bit of a weirder one. It involves this little bit of a weird concept here. Well, actually, I shouldn't say that the concept is weird. It's just the greatest common factor is going to be a little bit different. Okay. But I'm still going to identify that I've got 2 terms. I'm going to subtract one minus the other. And we just need to notice here what they have in common. Okay, so we talked about this in the last video, but there is a special type of polynomial term that these 2 have in common, and it is a binomial. Remember, a binomial is a 2-term polynomial, and if you look at both of your terms, it looks like they definitely have a single copy of that binomial that they can both give up. The first term can give up a single copy of x plus 1, and so can the second term. Okay, and I'm running out of room there off to the side. I'm going to go ahead and continue down the page here. So when we write our GCF, that's simply just going to be x plus 1. We're going to write our GCF times the leftovers here. So this 2 right here doesn't really have anything else in the denominator that it can combine with. So I'm just going to go ahead and copy down a 2. And then when I had 2 copies of x plus 1 in the top, it's going to subtract exponents with that base of x plus 1 at the bottom. So I've got 2 minus 1. That's just going to be a single copy of x plus 1 that I'm left with in that first term. Okay, and then there goes my big minus. And then in that second group, you can look at this as, well, I had x plus 1 on the top, I've got x plus 1 on the bottom. Those would cancel out and just simply leave me with x. And so now I'm here, okay? It's at this point that you want to look closely at those leftovers, because I think you guys from Algebra 1 got really good at being able to know it when you see it whenever distributive property comes up. And that's definitely something that happens here. We have a value of 2, and it's being multiplied times this binomial expression, x plus 1. So we're going to distribute that in, and then we're going to combine any like terms we might see. So here in the next line, I'm going to go ahead and say my GCF, x plus 1. Distribute that 2 in. I'm going to have 2x plus 2, and then minus x, okay? And so after we do that distributive property, you may notice that we do have some like terms going on here. I've got 2x minus x, and so we can go ahead and write our final answer as x plus 1, the GCF from the very beginning, times, I had 2x minus x, that just makes a single copy of x, and then plus 2, and that is going to be our final factorization there, okay? So be on the lookout for these problems where what your terms have in common is a binomial, okay? Here's another example, okay? So we've got the addition or the sum of two terms, a first term plus a second term, and we just want to look and see what they've got in common. We've got coefficients here of 3 and 4. Those don't have any common factors, but we do have this common binomial factor. We have an x minus 2 base in both of these terms, but you'll just notice that in both of these terms, they're being raised to different exponents. In the first term, it's being raised to the 1/2, and the second term, it's being raised to the 3/2. So we're definitely going to factor out x minus 2 in both of these, but it's going to be to the lower of the two powers that we've got. Okay, so the smaller of the two powers we've got 1/2, we've got 3/2. The smaller of the two powers there is simply going to be 1/2. So I'm going to factor that out of both of my terms here, okay? And that's going to represent my GCF. So I'm going to go ahead and write this as x minus 2 to the power of 1/2, and then times the leftovers. So what am I left over with? Well, in that first group, I had x minus 2 to the power of 1/2, canceling on the top and the bottom, just simply leaving me with that 3. And so I'll write my big plus sign, which I circled earlier. And then what happens over here? Well, that 4 doesn't have anything to combine with in the bottom, so we'll just go ahead and write 4. But keep in mind here, we have like bases, right? We have a base of x minus 2, a base of x minus 2. So when we divide like bases, we need to remember what we do with these exponents, okay? And the answer to that question is we would simply go ahead and subtract those exponents here. So I'll just go ahead and write this off to the side here. Whenever we are doing this, we're going to have the 3/2 from the top minus the 1/2 from the bottom. So that's 3 minus 1, that's going to make 2/2. And 2/2, that's just 2 over 2. That's just going to make 1. Okay, so that's interesting. So I'm going to have a base of x minus 2 to the power of 1 here. Well, anytime I have an exponent of 1, we typically don't write that because an exponent of 1 just signifies that I have a single copy of the base. And I can signify that by just writing down that single copy. So I'm not going to write an exponent of 1. That's what I'm going to have for my leftovers here. So again, I think we got you guys to a good point where when you see distributive property, you're going to execute it, right? So let's go ahead and do that. We'll distribute in a positive 4. And in the next line, we'll say the GCF x minus 2 to the power of 1/2. And then that is going to be times 3 plus 4x minus 8. Okay, and then I got some like terms there I can combine, just like in the last problem. I had positive 3 minus 8. It's going to turn into a negative 5. So this is how I'll write my final line here. I'm going to go ahead and say the GCF, the x minus 2 all to the power of 1/2, times, I'm going to put the 4x first because that's a positive 4x. And then when I do 3 minus 8 is a negative 5. So I'm going to say minus 5 here. Okay, and then I'm going to box that. That is my final factorization on that problem. Okay, so talking through a little bit, using a little bit of color, but when you factor out a GCF, that's the idea. You just want to look at how many terms you've got. You want to take a look at what you can factor out of each one of those terms that's the same. You also need to make sure that you're factoring out the biggest or the greatest common factor that you have in all your terms. Okay. So I'm going to go ahead and move on to some of these other examples here. Number 7, it says z squared minus 9. So if you're trying to look at this as what we just did, right, we have this big minus here, and I've got the subtraction of two terms, okay? So I've got one term minus another term here. This is where we would look and see if we've got a greatest common factor. Well, z squared doesn't really look like it has any common factors with that 9, and so we might determine here that we don't have a GCF. Okay, and that's fine because if we look over here again at our factoring checklist, just determined that this is an example of that number 1 is not really a thing. Okay, so really no factor that we can factor out of every single term. There's no GCF. So that means we're going to move on to the next little section here, and it says step 2, we need to count the number of terms that we see and then match it up to one of these 3 forms. It's either a difference of squares or sum of 2 cubes or a difference of 2 cubes, right? And so when we say that, what we are going to mean here is that you need to be on the lookout for any one of these forms that show up here on the left-hand side. Okay, maybe the example I give you is going to match these forms. And what are the distinct characteristics of these forms? Well, first of all, they only have 2 terms. So you have a u term and a v term. You notice those exponents are pretty distinctive, right? In the case of difference of squares, that's what I've got is some things being squared or some exponents of 2. In the sum and difference of 2 cubes, I've got exponents of 3. Those are some pretty distinct characteristics. And then I've got this operation in the middle. I've got the minus sign in the case of a difference, or I've got this plus sign in the case of a sum. Okay, these are all distinctive characteristics and hints or flags that you need to be on the lookout for so that you can notice the structure. And I would say that what makes some of these problems a little bit challenging is just straight up noticing the structure when you see it. Okay, and so in our example, it said z squared minus 9. I think that is a really good example of this first formula here, okay? And this is something that we call the difference of 2 squares, where if we notice that form on the left, we can automatically apply this factorization to the right, okay? So that's just going to be picking out what u and v are and then just saying u plus v times u minus v, okay? So let's actually go back to our example and actually apply that here, okay? So let me go ahead and zoom this in, and we've got our z squared minus 9. I suspect that this is going to be the form u squared minus v squared. And if it is, then that means it's going to factor into u plus v times u minus v. Okay, so if I suspect that that's what we've got going on, I'm just going to go ahead and set myself up here. So I'm going to go ahead and write 2 sets of parentheses, one with a plus, the other with a minus. And then I just might ask myself, what's playing the role of u and what's playing the role of v here? Okay, well, u is the thing being squared in that first term. So u is the thing being squared. The thing being squared in our first term here is simply just z. So I'm going to go ahead and copy that down as what's playing the role of u. And then if you look closely here, playing the role of v squared in the form is this number 9. That means that v squared is equal to the number 9, and if you actually wanted to set this up as a little mini equation and solve it, you would just have to take the square root of both sides, and then you would find that playing the role of v is actually just going to be positive 3, okay? And so what that's going to mean is that playing the role of v is simply just going to be 3, and this is the answer that we're going to have for this problem, okay? And so this is how these work, is you basically just have to notice the structure when you see it, and once you notice it, you have to apply the structure in the correct way, okay? So let's move on to another example here, right? So some hints or some flags about what we're dealing with. First of all, you should be checking to see if we have a GCF. I don't think that you're going to find that we have one here, so we're going to move on to that next little section. We have 2 terms here, and so I am noticing a couple of hints or flags here. First of all, I'm noticing this big minus sign in the middle. I'm noticing that I've got an exponent of 2, and the other hint or flag that I notice here is I've got a number like 81 in the mix, and you may remember 81 as one of your perfect squares from that sheet of perfect squares that we took a look at, right? So these are all hints or flags to suggest that what we're dealing with here is going to be the difference of 2 squares, okay? And so that's going to be a skill you need to pick up, is being able to notice them when you see them, because once you notice it, you just have to apply the formula, which goes u plus v times u minus v. So let's go ahead and set ourselves up here. So we're going to have u plus v times u minus v. Okay, so we'll set ourselves up here. And then the only question now is what's playing the role of u, what's playing the role of v, right? Well, playing the role of u, that's the thing being squared. In that first term, I think it's pretty straightforward. That's just simply going to be x. So that's pretty easy. And then remember, sitting in v squared seat is this number 81. So if you wanted to, this is something that you could either do mentally, or if you wanted to write it on the page, you could. V squared is equal to 81. Just square root both sides, and you would get v is equal to 9. And so playing the role of v is simply going to be 9. And we're going to box that answer. Okay, so a common mistake that I see students make all the time is they just see that number 81 there, and they have a habit of just saying, oh, sure, playing the role of v is just 81. And then they'll say x plus 81, x minus 81. But you got to be a little bit more careful, because that's not v, that's v squared, okay? And so you have to apply that thinking whenever you do problems like these. Okay, next one, going to get a little bit more challenging to notice our forms here, but again, some flags, some hints. What do you notice? Well, I notice that I've got two terms. I notice that I've got a big minus here, so that's the difference of something. I notice that I've got an exponent of 2, and then I notice I've got some perfect square numbers in the mix. I've got numbers like 16, that's 4 squared. I've got numbers like 9, that's 3 squared. I've got a number like 1, that's 1 squared. So in all of these different hints and flags, I'm noticing that I've got perfect square numbers, I've got a big difference, I've got an exponent of 2. I very highly suspect that this is going to be the difference of 2 squares here. And if it is, we know exactly how that sort of thing factors. That factors into u plus v times u minus v. So let me go ahead and set myself up here because I suspect that that's going to apply, okay? So let me try to see if OneNote's going to cooperate here. Come on now. There we go. So one's a plus, the other's a minus. And so the question now becomes, what is playing the role of u? What's playing the role of v? And when you do this, I really want you to remember that u is the thing being squared in that first term. So if you think about a 16x squared, the thing that you square to get 16 is 4, and the thing that you square to get x squared is x. So this 16x squared here, this can be rewritten as 4x squared. And that is what's playing the role of u in this example, okay? Because if we match it up, these are the things that are being squared. Same question on that next one, right? That's 1/9 sitting there, but that's sitting in v squared seat, okay? So is there a way for us to take 1/9 and write it as something squared, okay? Well, we said before that 1 is just 1 squared, and 9 is just 3 squared. And so playing the role of v here, again, the thing being squared is 1/3, and that's why in place of v, I'm going to go ahead and write a 1/3 in both of those spaces, and that actually completes the problem. This is our result right here. It's going to be 4x plus 1/3 times 4x minus 1/3. Okay, so a little bit of thinking you're going to have to do. Once you notice the form, that's challenging enough as it is, but then we have to actually apply the form, okay? Similar example here, I'm seeing some perfect square numbers, I see a difference, I see some exponents of 2. This is pretty clearly going to be a difference of 2 squares, which we remember factors into u plus v times u minus v. So setting ourselves up here, squaring, what's playing the role of u and v in an example like this? I would really love to be able to erase this equal sign right here, but I just can't because my writing program is just really not letting me do that. So one's a plus, the other's a minus. Okay, rolling through the punches here. Here we go. What do you square to get 9x squared? Well, you square 3x. So 3x is going to go in these spaces. What do you square to get a 49y squared? Well, that's just going to be 7y. Okay, and then you're done, right? So I want you to get to this mode, or to this point where when you're doing problems like this, you notice the structure, which if you get enough practice at that, that's going to be something that takes you super quick. And then the old question becomes, well, what's playing the role of u? What's playing the role of v? So I can plug it into my factoring formula, and then you're done after that. Okay, super simple. Same thing on number 11. I've got u squared minus v squared. Okay, well, it's a little bit odd here because playing the role of u is actually going to be the binomial x plus 1. But it does have the structure we're looking for. This is going to be u plus v times u minus v. And there we go again with my pen colors. Come on, man. There we go. Oh, now I'm blue? Oh, come on. Okay, so u plus v times u minus v. Here we go. Okay, so what am I squaring to get u here? Well, again, we're going to start to throw some of these curveballs at you where we're throwing binomials in the mix where we're used to having single variables or monomials, right? So it's the binomial x plus 1 that's playing the role of u here. So I'm going to go ahead and write that in. So u is x plus 1. And there's the whole question there, Mr. T, do I need those parentheses around x plus 1? Well, keep in mind, we talked about this in the last video, right? We said that the only time where you really need those parentheses is when there is a negative sign in front of those parentheses. If there's not a negative sign, then we could just feel free to drop those parentheses here. So actually, I'm going to go ahead and rewrite this so that I'm dropping those parentheses because, again, following that, that notion from the last video, we don't need them since there's no negative sign out front, okay? But now, what's playing the role of v? Well, that's the thing that I square to get a 4, and that's simply going to be a 2, okay? And it would be at this point that I would box my answer, but because u is being played by that binomial, the way that I have this written out now, I have some like terms that I can combine. I can say positive 1 plus 2. That's going to give me x plus 3. And then that second binomial there, I've got a positive 1 minus 2. Well, that's going to give me negative 1. Okay, and there's my answer right there. I got to a point where I can no longer continue to simplify either of my factors. So there we go, right? Be on the lookout for when your u or your v is a binomial, like maybe say here in this next example. All right, yet again, we've got a number like 9. It's a perfect square number. I have the difference of two things. I see an exponent of 2. I very highly suspect that this is going to be a difference of 2 squares. And so if it is, I should be able to factor it like this. And so let's go ahead and take a look at that, right? So playing the role of u and playing the role of v, let's investigate. So I think the u one is pretty straightforward. That would just be 3. I think we're at a point now where we could just go ahead and write that down with no problem, right? But now what's playing the role of v? Well, playing the role of v, that's a thing that's being squared, and here that's a binomial, okay? And now again, we ask the question, do we need the parentheses around that or do we not? Well, when we plug into that first term where there's just a plus in front of the space I'm supposed to write, I don't need those parentheses at all because that's not a minus sign. But in that second set, there is a minus sign there. So I am going to go ahead and need to have those parentheses around my x minus 1 because, again, the reason we said in the last video is that this negative sign is going to have to be something that you're going to need to distribute to both terms inside. And that's going to change some signs for you. So in that first term, I've just simply got some like terms that I can combine there. I've got a 3 minus 1. That's just simply going to give me a 2. So I'm going to write that x first, plus 2. But in that second term, I'm going to have something that looks more like 3 minus x plus 1 after I distribute in. And then my like terms there are simply going to be 3 plus 1. Okay? And so let's go ahead and write that. That's going to be x plus 2 times 4 minus x. And that looks a little bit odd because especially in that second binomial, I've got my constant coming first and then my x. So what you could do is you could actually factor out a negative 1 from that second factor. Okay? You can make it look like this. You can make it look like x plus 2, the binomial, times, factor out a negative 1, and then that would look like x plus, or sorry, not plus, goodness, that would be x minus 4, and that looks a little bit ugly in and of itself. So what I might do is I might just go ahead and write this, this extra factor of negative 1. I might just go ahead and write that out front. So I might have this. I might have negative x plus 2 times x minus 4, and that looks a lot cleaner than what we had in the previous lines there, okay? Be on the lookout when playing the role of u or v is going to be a binomial, okay? So some special things are going to happen whenever we apply our forms in these cases. Moving on to 13, looks like I've got something different going on here. I do have 2 terms. I have a sign, but and it looks like I have an exponent of 3, okay? So these are all kind of hints or flags that it's not going to be a difference of 2 squares in this case. We need to back and investigate because look at it's something different. It's going to be the difference of 2 here. And hopefully my computer will catch up here. There we go. Okay, so see if this will pull up. There we are. All right, so again, this is going to be an example. We had x cubed minus 8. So that's not going to be this first form any longer. Instead, that's going to be this, this form that we have down here at the bottom, okay? So we have u cubed minus v cubed. That's the form that we've got now. And if you take a look at the factorization for this, it is a little bit longer than we're used to, but I want you to realize here there's really nothing that's... There's just more stuff to do, right? So once you figure out what's playing the role of u and v, we have a binomial times a trinomial. And in that binomial, that couldn't be easier. It's just whatever's playing the role of u minus whatever's playing the role of v. And in that trinomial, you'll notice that it starts off by taking u squared. And then in the middle, we've got to figure out what u times v is. And then we follow that up with whatever v is squared. Okay? So again, there's more things to do whenever you move on to a difference of cubes or even a sum of cubes. You'll notice those formulas are pretty similar. But I wouldn't call any of it any difficult than, or any more difficult than what we've already done, right? It's just applying a different formula and plugging in u and v in different ways. So this is going to fit the form of a difference of cubes, u cubed minus v cubed. And since it is, we know how it factors according to the formula. This would just be u minus v times u squared plus u times v plus v squared. Okay? So once we figure out what's playing the roles of u and v, we can go ahead and set ourselves up here and then actually plug them in, and then we'll be all finished up. Okay? Well, playing the role of u, again, couldn't be simpler, just like we did with difference of squares. It's the thing that's being cubed, and here that's x. So in place of u, I'll go ahead and put an x. and then playing the role of v, right? So v cubed is sitting in the number 8 seat. So if you wanted to, again, just like we said before, you can set up a little mini equation for yourself, take a cube root of both sides, and what you'll find is that playing the role of v here is actually going to be the number 2 instead of 8. Okay, so there goes a 2 in place of v. And then we'll move on to my trinomial here, where the first thing I need to do is take whatever u is and square it. Well, u was x, so if I square that, I'm going to end up with x squared. In the middle, I need to take what u is times what v is and write out the result. Well, u is x, v was 2. If I take x times 2, we typically write that as 2 squared. Or sorry, goodness, not 2 squared. I meant 2x. There we go. And then finally, we follow that up with plus v squared. Well, playing the role of v is just a 2. If I square 2, I get 4. And that is it for that problem. That is the simple factorization. So it is a longer formula to plug into, but again, I wouldn't call any of that any harder than anything we've already done. All right. This next one, some flags or some hints here. I'm seeing a plus sign in the middle of my two terms. I'm seeing an exponent of 3. And then I'm also seeing a descriptive number here like a 125. And if you notice, that's actually a perfect cube number. So this is actually going to fit the form of the sum of 2 cubes. And so I'll let you go ahead and take a look at your half sheet for the formula for that. But this is going to factor into the binomial u plus v times the trinomial u squared minus u times v plus v squared. Okay, so it's all a matter of noticing it when you see it and then applying the correct version of the formula here. Okay, so we're going to go ahead and set ourselves up u plus v times, and then there goes a minus in my trinomial and then a plus. Okay, so playing the role of u, right? So we notice here that u cubed is sitting in 125 seat. Okay, so again, if you forgot what this was, it was a perfect cube. This is actually what 5 cubed is equal to. If you forgot that, though, then set up your little mini equation and then take a cube root of both sides. Okay, but this is going to be 5 in place of u. And then playing the role of v, I think that's pretty straightforward here because v is the thing being cubed and y is sitting in that seat, so we'll say y there as well. Okay, and now we'll move on to the trinomial. We need to pick up with a u squared. Playing the role of u is 5 for us. So 5 squared, that's going to be a 25. U times v in the middle. Well, u is 5, v is y, so 5 times y is just 5y. And then finally, we're going to end up here with v squared. So playing the role of v, of course, again, was y, so that'll be y squared. And there we go. There is a complete factorization of that sum of 2 cubes. Pretty good. Moving on to one like 15 here. Very similar here. I'm seeing descriptive things like numbers like 27, 125. These are perfect cube numbers. I'm seeing exponents of 3. I see that I've got 2 terms separated by a plus sign. This is a pretty straightforward sum of 2 cubes, u cubed plus v cubed. And we're going to go ahead and apply the formula here, which I'm running out of room for there on the side, so I'm going to go ahead and continue down the page. I know that this is going to be equal to u plus v, the binomial, times the trinomial u squared minus v plus v squared. Okay? And so I'm going to go ahead and pick up here with plugging u and v are equal to. Okay? So, playing the role of u, what do you cube to get a 27? If you check your half sheet that I gave you, that is actually going to be a 3. So, 3, and then we'll say x, because that's a 27x cubed there in my first term. Plus v. Okay, so what's playing the role of v here? Well, it looks like OneNote is going to crash on me. Oh, maybe not. Okay, we'll try to finish up quickly, okay? So, come on, computer. Don't do this to me. Plus. My computer's being funny. Okay, I think we are normal again, hopefully. Can I write? Question mark? Plus? Okay, there we go. Perfect. Okay, what do we cube to get 125? That's going to be a 5y, okay? Because it said 125y cubed. That's my binomial. Move on to the trinomial now. Now, this is where I need to take u and square it, okay? Well, playing the role of u, we said, was 3x. So if I square a 3x, if I square 3, I get 9. If I square x, I get x squared. Okay, so a 9x squared is going to take the place of a u squared. I'm going to pick up with my minus, and then we want to do u times v. Well, playing the role of u is 3x, playing the role of v is 5y. If I do that, 3x times 5y, I'll do the 3 times 5, that makes 15. And then x times y, I would just write that out, x times y. And then finally, I need to finish up here by figuring out what v squared is equal to. Well, playing the role of v is 5y. 5 squared is 25. Y squared is, well, y squared. There we go. And there's your complete factorization. So you can start to see how some of these are going to get a little bit tricky, but again, it's all a matter of figuring out what's playing the role of u, what's playing the role of v. In this example, we had something cubed plus something else cubed. And those two things were 3x and 5y. So that's what's playing the role of u and playing the role of v, respectively. Okay? So that's some thinking you're going to have to do from problem to problem. Last one for the video here. We're going to skip 17 and 18 that you saw down below. We're going to save that for the next video. But here's the last one, right? So some descriptive things here, some flags, some hints, right? I'm seeing numbers like 8. That's a perfect cube. I'm seeing that I have 2 terms. I'm seeing that I have a minus sign, so that's a difference. And I see an exponent of 6 there, which is a little interesting. I might suspect that this is either the difference of 2 squares or the difference of 2 cubes. And the thing about it is that since 8 is a perfect cube, I suspect this is going to be u cubed minus v cubed. Okay? And if it is, we know how that factors. It would just be u minus v times u squared plus u times v plus v squared. That's what the formula says. So binomial times a trinomial there. So let's set ourselves up. So let's figure out, my goodness, my ink to shape is being very funny there. Okay. We're going to set this up. We're going to say binomial times a trinomial. We'll set up our operations there. And then here's the thing. What do we square, or sorry, not square, what do we cube to get the 2 terms that we've got here? Okay? Well, to get 8, you would just need to cube 2. Okay? So that's playing the role of v, so that means everywhere I see a v, I'm going to go ahead and put a 2. What do you cube to get x to the 6th? Well, if you think about that for a moment, that would have to be x squared because power to power means that I multiply those exponents, so that would be a 2 times 3. That would give me my 6 that I had originally, okay? So that would actually be x squared that is going to be playing the role of u. So again, that's the type of thinking we're going to have to do here in order to figure out what u and v are so that we can plug our things in, and then we'll be right as rain, okay? So that's the binomial. Now we move on to the trinomial, where the first thing I have to do is do u squared. Well, playing the role of u, of course, is x squared already. So if I have to take an x squared and then square it further, that would be x squared squared, and that would be x to the 4th, power to power, okay? Next is u times v. Well, playing the role of u is x squared. Playing the role of v is 2. If I multiply those two things together, I get 2x squared. And then finally, I got to pick up with a v squared, and that's just simply 2 squared, or in other words, just 4, okay? So I know I use some different colors there, but that would be our factorization, okay? So again, when you're using these factoring formulas, it's just a matter of, first of all, do you notice the structure when you see it? And then second of all, can you apply that structure when you see it? Okay? So it's a matter of noticing it, and then it's a matter of applying it. But I hope the examples we did in this video shed some light on how we do these in general. If you guys have any questions, then please let me know. We're going to go ahead and finish up factoring in the next video, P.4 Day 2. So good luck on the assignment. If you need help, let me know. And that's all I got for this video. Thank you very much for your attention, and I will speak to you in the next one.